Sí, podemos ir. Ok, ahora ya estamos por YouTube también. Sigue entrando gente, pero vamos a dar comienzo a la primera plenaria del día de hoy. Esta plenaria va a estar a cargo del profesor Mateo Parsani. Voy a tratar de hacer una introducción en inglés para él, así que para que él no se sienta excluido. I think we can start now, Mateo. Welcome everyone to a new plenary lecture of MECOM 2021. Today we are pleased to have with us Professor Matteo Parsani. Matteo was born in Cologne from an Italian family. He holds both Italian and German citizenship. At the age of 5, he returned with his family to northern Italy, where he started his studies. Matteo holds a master in aerospace engineering with a specialization in computational aerodynamics from Politecnico di Milano, and a PhD in mechanical engineering from Free University of Brussels. After a period of as a postdoc fellow at NASA Langley Research Center in October 2015, Matteo joined KAUST for King Abdullah University of Science and Technology, located in Saudi Arabia. Currently, he is an assistant professor of applied mathematics and computational science. He is also the principal investigator of the Advanced Algorithms and Simulations Laboratory and a member of the Extreme Computing Research Center. Professor Matteo Parsani's research interests are related to the design and implementation of novel, robust, and scalable numerical methods on unstructured grids for hyperbolic and mixed hyperbolic parabolic partial differential equations. Application domains that are currently driving his research are computational aero and gas dynamics, dense gas flow simulations, and computational aeroacoustics. His current main industrial collaborations are with McLaren, Boeing, Zapata Computing, and NASA. Without further ado, Matteo, you can start your presentation by sharing your screen. And you have 45 minutes for your lecture and 15 minutes for questions and answers from the public. Go ahead, Matteo.
Okay, thank you very much, Hugo, and thank you very much to the organizer for inviting me to give this lecture. First question, can you see my screen well?
Yes, perfect.
Okay, good. So as Hugo said, I'm connecting from Saudi Arabia, where I live and work with my family. And next to me, there is Lisandro Dalcin. Probably many of you knows him because he's from Argentina and used to work at CONICET. So in my talk, I'm going to give an overview of what should be the next generation of compressible CFD solver based on what official document, international document released by NASA and other entities. And I'm going to make the point of where the community is and where we are from our side. So, all right. So first of all, I want to thank some of the collaborators. There are many other people that I didn't mention here because of space and time. Those are the main one. The first one is Lisandro, who has been, a great collaborator in the past 5 to 6 years, and he's also a very good friend. Without his help, many of the things that we have now in the solver wouldn't be possible. David Fernandez, who was a former NASA postdoctoral fellow, also a colleague of mine during the time at NASA. Now he's at University of Waterloo. Then Bilal Hadri, which is a computational scientist at KAUST Supercomputing Lab, because at KAUST we have a supercomputing laboratory with one of the largest supercomputers in the world, Shaheen XC40. I want to thank the director, David Keys, and then all the members of the group that I lead, Rasha, Shema, Nada, Mohammed, Irving, Ahmad, former member like Diego from Colombia, Radwan, and Huashen. So I'll start, as you know, in my title, I said why, what, when, and how. Those were the 4 keywords. So I will start, first of all, talking about what's the plan, not only, our plan, but the plan at least at of a big, large community at the international level. So in 2014, NASA released the so-called NASA CFD 2030 vision, where, people from academia, for instance, MIT, Stanford, and industry, Lockheed Martin, Boeing, Pratt & Whitney, define the milestone which set the expectation where a CFD solver, mainly compressible CFD solver, should be by the 2030. And two key milestones highlight here in this slide. The first one is related to the wall model largety simulations, a mix between LES and runs. And the main important one, that's what we work for the past 5 years here at KAUST, is the production entropy scalable solver, which are expected to be to enter in production mode for at the industrial level and also government lab around 2027, 2028. So from that documents, the NASA 2030 CFD vision, many paper, many workshops were born. And recently there is an important paper of Professor Mavropoulos, who basically is also the main organizer of the CFD 2030 workshop at the AIAA conference, SciTech and Aviation. And in that document, one can read that, advances in computational algorithms have contributed equally or even more compared, to the advancement in hardware, which has followed, at least for 40, 50 years, the Moore law for HPC. However, because, usually the algorithm complexity, when one study the algorithm complexity, always talk about asymptotic properties. So the benefits of superior algorithm, they only start to become, evident nowadays, because we are pushing really, the border of our knowledge in terms of numerical algorithm and also in terms of physics for the development of new architectures. And the development of algorithm does not only require, the knowledge of applied mathematician or numerical analysts, but you also need to come together with physicists and also engineering, because those are the guys that eventually are going to take the solver, run it, and trying to figure out, what they are computing and the physical property of the problem, the solution, the coefficient, the lift, the drag, whatever is needed in the aerospace field. And unfortunately, during the past 2-3 decades, the development of fundamental algorithm has often been put aside in favor of incorporating in existing code more physics and more, complicated, multi-physics problem. And this basically has yielded detrimental, effect on the solver itself, because the algorithms that are currently available in software that companies use or that are developed and used at the national lab level, they are lagging behind compared to the physics that we want to resolve. And this has become a more prominent problem, which has been highlighted in the 2030 CFD vision. And like I said, more detail can be found in this paper of Professor Dimitri Mavropoulos. So why do we need then something different? What's the need currently in terms of algorithmic development? I state upfront that at least the answer to this question from my side requires some clear and very bold explanation that many people in the CFD community, they will have maybe partially hard time to digest. Simply because when you start to touch the topic of low order versus high order, you turn on many green light, but also red lights. So what I wanted to state, that's for experience that I have here at KAUST, but also during my time at NASA, and also some of my colleagues, Lisandro, have, is that there is a large family of problem in at least compressible CFD, where it has been shown, and we can still show that high order scheme, adaptive high order scheme, can be much faster compared to second order methods. And those are mainly problem that are where we try to resolve the scale resolving simulation, such as large edge simulation, aeroacoustic problem, where small scale and long time integration are needed. So here I'm just going to give a kind of simple problem to explain that, to give a point to the fact that high order scheme are better for some problem compared to the low order one. This is we have come up with a method of manufacturing solution. The solution is shown here. It's given by the sum of sine and cosine and some exponential as a function of space. It's a supersonic flow where you have an area where the flow goes supersonic and zone where the flow is subsonic. There are no shocks. The flow is completely smooth. This is the best, situation context where high order scheme should shine. And what you basically see here on the right-hand side, there is a log-log plot where on the y-axis, we are plotting the L2 norm of the error for the density. And on the x-axis, the wall clock time in hour. So the red line is associated to a P1 scheme, which is a second order scheme. The blue one is a fourth order scheme. The purple one is a sixth order scheme. And finally, the green yellow one is an eighth order scheme. And if you, for instance, enter this graph, the view graph at this point between 10 to the 6 and 10 to the minus 8, which is an accuracy that at the engineering level is sought, you can clearly see that when you enter here and you draw a straight line, the first thing that you're going to encounter is the P7 one, which is an 8th order scheme, okay? And that one will give, as you can see, the error that you want in the least amount of wall clock time. Obviously, if you go a little bit up between 10 to the minus 4 and 10 to the minus 6, the first one that you encounter is probably, the 6th order scheme, and you go all the way up. And when you are around, 10 to the minus 3, 10 to the minus 2, the one that you encounter are typical second order scheme. This is it for a specific problem, okay? A very smooth solution, metal manufacturing solution. We have found out that, for a realistic problem, such as the flow around the delta wing, which was placed in a wind tunnel. So we have experimental data which are reported in this paper, which is number 44. Basically, we ran our solver, which is a 6th order scheme. It's not only a 6th order scheme. We have a 2nd order scheme in the blue region. We have a 3rd order scheme in the green one and a 5th order scheme in the purple one. You can see it here in the top left plot. And here we bootstrap the simulation on the supercomputer, and then at a certain point we start to gather statistics to collect, the average of the CP. And what you can see here on the most right plot is the comparison of the distribution of the CP, minus CP actually, against the experimental data that were measured in Munich, in one of the wind tunnel in Germany. I think it's one of the DLR wind tunnel. And what I want to highlight is that here we were using, 1/2 of the degrees of freedom that are used for the finite volume code that was used to compute, for the first time the solution around this flow. And we were about 2.2 times faster compared to the finite volume solver. Again, this is not always the case, but for some problem, especially for LES, where you have small scale, or for other acoustics, high order method can be, the winning card. So then one could say, okay, what's the problem? Have high order scheme, they have been around forever. You can look back at the masterpiece of Zhang, Quarteroni, where they describe spectral element methods, which dates back around the 80s and 90s. And since that time, many advancement has been done for the industrialization of high order scheme. Specifically, the German Aerospace Center, the DLR, has its own high order code based on DG, formulation discontinuous Galerkin. NASA LARC has its own DG code, AIMS as well. Then there is the big group of ZJ Wang, a professor at Iowa State University, who has developed during the last 5 to 6 year HP music, which is an adaptive HMP adaptive solver, which has been also used and is currently being used by General Electric to perform simulation. There is the masterpiece of the group of Peter Vincent from Imperial College, which is called PyFR, based on Python kernel for the flux reconstruction scheme, which scales very well on supercomputer, which are equipped with GPUs. They even got close to win the Gordon Black Prize, I think, in 2016. Then it's us with the SSDC algorithm that we are partnering with McLaren, Boeing, and Airbus to solve, challenging problem. There are other group at the MIT with the Aero Astro Lab that have their own DG code. So what I wanted to say is that this field has been very active in the past few years and is still very active and is getting even a more impetus during the beginning of 2021. So then again, one could say, okay, what's the problem with high order scheme? Matteo, you're telling to me that all of this group, they have it, they can run it. So what's the problem? Well, the problem is that, you have to babysit these codes, especially, codes which are based on standard formulation of a DG scheme. Here, I'm trying to give an explanation or a justification of why something else has to be done, in the sense that, high order scheme, they're very well suited for a smooth solution, but they suffer heavily and a lot when of instabilities, when they're used to simulate flow where you have discontinuities or under-resolved physical flow feature, like it could be under-resolved turbulent flow. And here in one of our work, we were running the standard problem, which is the Taylor green vortex at Reynolds 1600, Mach number 0.05, almost incompressible. And in this table, I black out the first part, and you will understand why later. So in this second part, we were running what we call the split form DG, which was introduced in 2016 formally by Gasnet, but at the same time also by Mark Carpenter, senior research scientist at NASA, Langley. And on the bottom part, we are simply doing the standard DG. We call it DC because it's the standard collocated DG. And what we did here, we basically use different degree polynomial for the solution from 1 to 15, so a very high order scheme. And we use different mesh, a cube, with different number of elements from 3 cube to 48 cube. And what you observe is that for the split form with Kennedy and Gruber, KG stand for Kennedy and Gruber, everything works fine, as one would wish. When you start to go, with the standard DG code, collocated DG, what you observe is that, you really have trouble when the mesh is coarse, and because you are basically dealing with under-resolved physical feature. And on top of that, at the cell interface of two elements, is like there is a jump on the solution, and in many cases, when the mesh is very coarse, that becomes like a weak shock. So you can consider it like a small discontinuity. This is for the Taylor green vortex. We run the same things for what it is called in literature compressible homogeneous isotropic turbulence. And again, the first part is, blackout. I will show you why later. And here we started to see that even, the robust split form Kennedy and Gruber approach start to fail for a low order polynomial and, a very coarse grid. And the standard collocated DG fail almost everywhere except for very high order polynomial, the fourth order polynomial, and, very fine grid. And you can see here on the right, the kind of solution we were trying to compute, where we show the path line on the surface of velocity. So there are very, very fine small scale. So it's a flow at a Reynolds number of 194 and a turbulent Mach number of 0.62. And inside the flow, we have shocklet. So small shock that connect, a turbulent feature. So the point is the following: if we cannot resolve the Taylor green vortex and we cannot do the compressible homogeneous isotropic turbulence, what's the hope that with high order adaptive scheme we can, solve the very challenging problem like the NASA Common Research Model, Siemens next generation of gas turbine, the X-59, for instance, airplane, which is, a low boom supersonic airplane developed by Lockheed Martin and NASA. And even not in the aerospace sector, General Electric is coming up with a new family of wind turbine, which are as tall as the Eiffel Tower, with blades which are 260 meter long, and at the tip of those blades you definitely have a compressible effect, so you must be able to deal with things very properly. Here is one of the Formula One car that we have been dealing with because we have a partnership with McLaren, and here is the former Delta Wing, that's DLR Delta Wing. So in order to handle, these kind of problem during the last decades, several techniques has been used, like filtering. You go up and down with your polynomial and trying to smooth out, the feature that you cannot resolve. We know algorithm, artificially dissipation, over integration, and limiter. Unfortunately, all this technique, if you go in literature and if you talk with somebody who is in industry and is dealing with complex geometry, they don't work, and they are very problematic when you go unstructured grid. And they're requiring tuning parameter. They work for a certain set of problem, and then you need to tune the knob to make the scheme working. So this is not what industry, and this is not what we want to have when we run large scale problem. So what do we do then? So the answer has been around for a long time, and it's the nonlinear stability. In the case of the Navier-Stokes equation, is the so-called entropy stability that now, just a few months ago, we can achieve both in space and time, and also positivity preserving. But like I will say later, positivity preserving is fundamental, is one of the backbone of the requirement for nonlinear stability, the entropy stability, but so far has not harmed us badly. Okay, so in this talk, I will focus mainly on entropy stability. And here I'm bringing back, the table that I showed you before, just to show you that if you go with entropy stability, you can achieve something which, we can consider like the holy grail of CFD. So kind of robustness. We are still cannot show convergence of our algorithm to a weak solution and so to a physical solution, but we are not, too far, or at least we have moved one step forward. And in the first rows of the table now, you can see what I covered before, which is what we call entropy stable scheme, ESC. And for all the grids polynomial that, for all the solution polynomial that we tested, and for all the grids for both problem, we achieve, 100% of the robustness. So the solver never blew up. In addition, we run a 3D problem, which is a supersonic bar. So here you just see a cross section, but it's a supersonic bar at Reynolds 100,000, Mach number, upstream Mach number 1.5. There is a strong bow shock here, and in the back you have instability, and then turbulent flow is generated here. And here you also have reflection of shock and a weaker shock. And what you can see here, you can see the comparisons. The blue line is the split form, Kennedy and Gruber, and the other one is the fully entropy stable scheme. And you can see that at certain points, the Kennedy and Gruber give up. We get not a number, it blows up. Whereas, the entropy stable scheme ran to completion. And here we were plotting the drag coefficient related to the pressure drag coefficient part. And here is the viscous one related to the skin friction. And on the side, you can see, a snapshot of the flow field corresponding to the Mach number, corresponding to the Mach number distribution. So, which are the ingredients that we have in our toolbox to develop a scheme which are entropy stable, and they can be sharply proved that are not linearly stable for both space and time. First of all, I want to highlight that we are dealing with discretization, which is based on the method of line approach. So we first discretize in space, then we get a system of ODE, and then we integrate it in time with, for instance, Runge-Kutta schemes. So, and the geometry that we want to tackle, they are really complex. So I'm showing here on the top the front wing, for instance, of a Formula 1 car of, I think it's 2018 Formula 1 car is very complex. You need to use unstructured grid, and the flow that is generated by this, device is extremely complex. And on the bottom is again the NASA Common Research Model, which is one of the grand challenge in the NASA 2030 CFD vision. So the ingredients that we have, of course, are the Navier-Stokes equation. We want to deal with the compressible Navier-Stokes equation, 3D. We have the summation by parts operator that we can construct of any order. We use the simultaneous approximation term to impose boundary condition and to patch together interface, because we use this continuous method like DG method. We want to use HP non-conforming interfaces and being able to adapt on the fly our solver, because we are seeking to compute solution that we don't know, very well. So we want the solver to be smart enough to capture, the feature in region where they are important to be captured. And we also want in time integration scheme, which are, adaptive in the sense that they adapt their time step based, on the error on the tolerance that we want to achieve. And of course, all of this has to be put in a high performance framework, in the sense that the problem that we are solving here, they cannot be run on a simple laptop on MATLAB code. They really need to be written in a specific language, Fortran, C, maybe Python or whatever, but they really need to be, written in a very efficient and scalable way. So I will try to give an overview here of the main ingredients that we have to construct, this high order scheme. And I will start with the advection diffusion equation, because many of the key ingredients, they can be understood, or at least they can be, seen at a high level for this simple problem. So we have our equation, in multiple dimensions, in this case, in 3D, x1, x2, and x3, we have our, hyperbolic contribution, which is the inviscid part, and then we have the viscous part. Of course, we need to equip the problem with boundary condition GB and initial condition, which is the G0. And usually what we do, we don't solve problem in Cartesian grid, because we are aiming to use a fully unstructured grid. So we transform each element in our domain, we map it into the standard element. And, this is simple, the derivative going from the physical space XM to the map coordinate system xi L. So by using this, the chain rule, basically, what you do, you replace the derivative in the XM direction with the derivative in the xi direction. You plug in this expression into your original equation, and what you end up having is the bottom figure, where the last term on the left-hand side and the last term on the right-hand side are basically zero by what we call the geometric conservation law constraint. Basically, because the sum of the derivative in the xi of j, which is the Jacobian, the determinant of the Jacobian, times xi L, xi m are zero. And you can see this term also appearing here. So those terms are also zero. Okay, so we can drop these two terms, and what you end up having is this strong conservation form, of the equation. Fortunately or unfortunately, it can easily be shown that if you try to discretize right away this equation, okay, in this form, you're going to get a scheme, at least when you use SBP operator, which is unstable. You cannot prove stability of it. So what it is known in literature is to use what we call the canonically split form, where you basically take 1/2 of the divergence form, okay, and 1/2 on the chain rule form, this one here. And then for the diffusive part, you take the conservation form. So you don't basically do anything. Now, if you discretize this, equation now with, with the scheme, in our case, the SBP operator, you get a scheme that is provable, stable. In this case, we are in the linear case, so we talk about energy stability. So how do we do that? Well, we introduce what is called, since the 70s, with Gustafsson, Bertil Gustafsson, a guy from Sweden, the summation by parts operator. And in our case, we recast the collocated discontinuous Galerkin, scheme into this framework, into the SBP framework. So I'm not gonna state here, and read this formula. You can find it in paper. But what basically the differentiation operator D, in this case D1D, because I'm stating it for the one dimension, is doing, it differentiate exactly monomial up to degree P. That's the main, properties of it. And of course, it can be written as another matrix P inverse times Q, where P for finite element people, you can see it like, is the mass matrix, okay? And then we go multi-dimension using tensor product element. At this point, people, maybe they will ask a question later. They can say, okay, so how can you deal with, tetrahedra or pyramids? Well, there are several reasons why we deal only with tensor product element. I do believe, and we believe, that when you have, if you can start with a coarse mesh made up by tensor product element, and then you have the automated HP capabilities, then we can mesh and we can resolve, all the, geometry that we want. Of course, we need to start from a mesh which is hexahedral base mesh, and sometimes for complex geometry that is very hard. So what we usually do, we end up having wedges or that we chop, and the mesh is not completely perfect, but at least we have uniform, we have hexahedral element, everywhere. So this SBP operator can be, a little bit nasty to understand if you are not familiar with it, but I want to give you, the key idea. So in many proofs that we have at the continuous level for the PDE, we use integration by part rule. This is also used very frequently for finite element people. And what you basically do there, you define an inner product, between two functions, V and U, and then you define a norm, which is in this case is U squared and the integration. And what you do, you apply the integration by parts where you have, the inner product of your function v times the derivative of u, and then you can recast it in this way. Summation by parts, they do exactly the same things at the same discrete level. They are mimetic operator in this sense. So you define an inner product with the matrix P in between. So here we talk about, the norm. The P is our P norm. We use it to compute the inner product, and we also use to define the norm itself. Okay, but there is one-to-one mapping between what you do at the integration by parts level, at the continuous level, and at the discrete one with the summation by parts. And you can see here that you have your inner product, and you have boundary term, which correspond to this term up here, and also then another volume term, which pop up from the integration by parts. So it's really mimetic in this sense, and this is a key properties that allow to construct provably and in a sharp manner, energy stable and also nonlinearly stable algorithm. So then we use this SBP operator, we plug them in our advection diffusion equation, and this is what we get. Okay, you see here in blue are the metric term that they need to be computed at the discrete level, and J is the Jacobian of those metric terms. Why do I highlight them in blue? Is because those are key ingredients that we use in the case of conforming interface. So where, the interface between two elements is shared by two elements which has the same polynomial degree. These elements are also used when we construct HP non-conforming element. So what we do in that case, we construct a simultaneous approximation term at the interface to patch together the two interfaces. And one of the key elements are those metric terms. Okay. And here also we have this term which I put in red, which goes to zero via the geometric conservation law. Okay, so actually this is the expression that we have. Okay, we have this is the expression that we have, but it's not the one that we implemented. The one that we implemented is based on the local discontinuous Galerkin approach. And I stated basically here where we have, the inviscid part, the viscous part, where theta is now the gradient of my, variable. And we have the inviscid sat and the viscous sat for the computation of the boundary condition and the interface coupling. And here I state, the problem, the minimization problem that we use to compute, this matrix term. Okay, the same things can be done, can be taken and implemented or applied to the compressible Navier-Stokes equation. The key things here is that the compressible Navier-Stokes equation, they have a convex extension which depends on what we call the entropy function, which is nothing else than the density times the thermodynamic entropy. And mathematicians, they like to put a minus in front of it. Okay, why we are interested in this quantity? We are interested because if you can bound the entropy function, then that bound can be converted into a bound of your solution on the norm of your solution, which is in this case it's the norm, which is the integral of my solution Q at the time Tf Q transpose dot Q, and this is bounded by a constant independent of the solution divided by the minimum of the Hessian plus some term which depends on the initial condition. And you can find a plethora of work related to this, starting from Lax, Dafermos, Tadmor, and many more scientists. So what we do, we take the Navier-Stokes equation, we write them we map each element in the reference element. And what we observe is that we still have a term which goes to zero because of the geometric conservation law. A key ingredient here is that we recast the viscous term in terms of the entropy variable, which are the W variable here. And how do we show that these schemas are entropy stable? You can read paper, outside, but basically what you do, you take your equation, you dot product them, with the entropy variable, you do the algebra, and what you end up having is basically a statement of, the variation, how it's an ODE for the entropy function integrated over the volume. And what you can see here is that you have boundary term, like you have when you apply the integration by parts to any expression, okay? You have inviscid contribution and viscous contribution. This is, again, it's a key ingredient, and if you use summation by parts operator, you can mimic those terms. So this is the full discretization that we use. I'm not gonna show, all the details because it is a lot of algebra, but those are the steps. You basically construct the gradients of the entropy variable theta. you compute the divergence of the inviscid flux through a 2-point entropy conservative flux. You compute the viscous term, you implement the coupling between two elements, and then if you want, you can add dissipation in terms of entropy. It's not necessary, but it adds an additional layer of robustness. And all of this was extended, by Haas and the collaborator in 2020 for HP non-conforming interfaces. So what I want to show here is not the algebra, but if you compare what we get at the continuous level, which is the top expression, and the one at the bottom, which is at the semi-discrete level, we actually have this term, which correspond to the integral of the entropy and the time derivative of the integral of the entropy. We have dissipation term, which is the one that appears in the Navier-Stokes equation. And here, what we call, eta is the sum of the inviscid contribution at the interface and the viscous contribution. So we mimic really one-to-one what is happening at the continuous level. So here is just to show that the scheme is, the solver is the full solver is design order. We run fourth order scheme and for different time integration, and we get in the L2 norm, that's what we measure the expected order of convergence. This is for the supersonic flow in a box. Here is the conservation of entropy. We run the compressible Euler equation on this cube with distorted element, different degrees. So it's a non-conforming. And what you see here is that we are preserving the entropy to machine precision because we have 10 to the minus 13. Here is, for the Navier-Stokes equation, again, we have a lead cavity flow. The plate is spinning. We have two contributions in the equation, which is the orange term and the blue term. You sum them up, and we get 10 to the minus 18. Here is to add, more complication. We have a rotation of the plate, and on the side, we are injecting or subtracting, heat. So we have additional contribution, which are reporting in this first plot. You sum them up, and again, you come up with a number, which is 10 to the minus 13. So we preserve the entropy up to machine precision. This is not just a coincidence. That's what the proof tells us. So what do we do in time? I will have to rush because probably I will run out of time. So what we do in time, we developed recently a new family of Runge-Kutta scheme, which we call relaxation Runge-Kutta scheme, that are very easy to implement. And the only difference that you have in this scheme is it in the last, step, when you update your solution here, where I have my mouse, you have a parameter gamma n, which you compute in such a way you can preserve any convex functional, which can be entropy, any energy, anything that you want to preserve. And the solution of this, gamma is the solution of a nonlinear scalar algebraic equation, okay? So here we show again that with the fully discrete scheme, we are a design order for fourth, fifth, and sixth order scheme. You can see that the convergence rate is 4, 5, and 6 here. And here is the entropy preservation at the fully discrete level. Here we run quadruple precision. You can see that we preserve the entropy to 10 to the minus 31 because we are running in quadruple precision. This is with relaxation. Without relaxation, you can see that it's plateau, but if you let it run longer, the computation will blow up because the entropy will start to increase, drastically. Here is another problem. I will rush through it, but to show that we also, can take into account a source term from one side, for instance, in this case of a cube. And here is just to show you that, the value of the gamma, according to the theory, should be, around 1. Don't be misled by this value 0. Here you have 0, 10 to the minus 6 plus 1. So the value of gamma, in order to be accurate, has to be, the scheme to be accurate, has to be around 1. And we test this for the supersonic bar that I show at the beginning. So here it's some test that I wanted to show simply because the solution of nonlinear algebraic equation is not a done deal. Sometime coming up with a good method that can compute that gamma factor is very complicated. And here we also have done some scalability study up to 10,000 core to show how different methods perform, because we want to find, the best method that we can run in production mode. In this case, for the full aircraft, for the NASA junction flow. So the code that we develop is called SSDC. It's based on PETSI and a P forest for the adaptation. And it really required a good synergy between applied mathematician, physicist, and computer scientist, because you cannot get a code just out of pen and paper physical properties. So you need to do something even more at the computer science level. So Here is the performance of the code. We report weak scaling and strong scaling. Weak scaling, we are performing, as expected, how to say, efficiency around 85% for the fourth order, which drops a little bit for P7, not because the algorithm is not performing well, it's because we ran on Shaheen, not in dedicated mode. So there was, network congestion. And here is the strong scaling. We are doing very well in the first, 3/4 of the table. Obviously, when we run on 65,000 core, because we basically have between 5 to 15 elements per core, so basically nothing, the efficiency drop all the way to 35%. But this is something expected. There is not enough work to be done per core at that level. So I will show here. I will go through some test cases. More and more complicated. This is a supersonic flow, Mach number T.5 around the cylinder. We compare, the SSDC results with the, numerical results and the shock wave theory, and we are on top of it. Okay. So here is the so-called Chardin problem. It's again large Mach Reynolds number, and a large Mach number. And the first time we look at this picture, we were really astonished. You can see the top part is experimental data, and the bottom part is the computational shadow graph of the flow around this object. And you basically can't distinguish what is what. We can really capture very good feature in the flow. Quantitatively, we can compare our simulation with experimental data, with the ray shock theory, and we are also there on top of those results. Here is a very extreme flow that we compute in collaboration with Airbus. Is the Valeo control diffuse blade at a very realistic Reynolds number and compressible Mach number at two different angle of attack. The first one on the top is 4 and the other one is 7, and you can see that there is a huge change in the separation at the nose of the geometry, and also the structure are very more fine scale in the case of degree 7. And here we compare the value of the mean pressure coefficient for the two case, angle of attack 4 and angle of attack 7, and we compare it with numerical result and experiment. And again, also there, even though we were using a very coarse mesh, we are on top of those results. Finally, here I think is the last test cases is the NASA junction flow, which is one of the last cases that we ran with the SSDC very recently, and we use also to exercise all the feature in SSDC. It's a real Reynolds number, I would say 2.4 million, a Mach number, which is close to the region where you are, it's not really takeoff, but it's during, where you're climbing up during to reach the steady state altitude when you want to fly with an airplane. And here we use an adaptive code where you use second order, I think third order and sixth order in the region near the body. And what we observe here is also that we compare the experimental data with the SSDC simulation, and we capture them extremely well, but that can be done with a very fine mesh. But what I want to highlight here is that we were capable of running a simulation at the cost which is very close to a very well-known code which has been used for many years, and was recently also published some results in the ISI Tech 2021. I don't want to give any name here. You can send an email to me and I can point you directly to the papers that I'm referring to. So even though we are using an adaptive code and we are just running at CFL 1, but we know that we can go way higher than that, because we can reach something like which is between 1.8 to 2. We are really competitive, and in terms of computational cost, if we compare our simulation with standard second order or second order find a different simulation. So with this,
Matteo, sorry,
yes.
You have 2 minutes or so to round off your presentation.
Okay, thank you very much. So I'm basically done. This is the last slide. Conclusion. So currently we have the first prototype of compressible CFD solver that will form the backbone of the next generation of a CFD solver, has stated, has listed by the NASA 2030 document. There are still big, big issue to solve, or big challenge to solve, not issue, let's call them challenge, is a more positive way. One of them is positivity, but so far, positivity has not harmed us. We know how to solve this one. We are working on this. It was not so far one of our highest priority because it really didn't harm for this complex flow problem that we are trying to run. It can create issue, but not, at least for the problem that, we are solving currently. We are integrating, like probably everybody else around the world, artificial intelligence and machine learning to enhance the capability of the solver. I can give you more information in a separate talk if you are interested. So thanks to, the outstanding skill of the people we are working here, mainly with Lisandro, we are optimizing, our code, or we will optimize our code for different architecture and each component of it, even though, the solver has already performing very well on CPU type of architecture, like we have it in here on Shaheen. So the big, huge, I don't know how to describe it, next challenge that we started to work on, and this is, a challenge that, all the community, probably many of the people in the audience are trying to solve, is related to implicit time integration scheme. Because even though we are not solving reactive flow, we have very stiff problem, which are, even made more stiff by the fact that we use high order scheme. If we add source term, because eventually, the code will need to handle also source term because of the chemistry or other, type of problem that we want to solve, then the stiffness will become even, larger. And so we need to solve even more complex, complex in terms of stiffness system of algebraic equation. And for this reason, we need to use definitely astable and astable scheme, and most likely we will end up using, implicit, explicit Runge-Kutta scheme in the context, if it's possible, of relaxation Runge-Kutta scheme, so that we will get a fully entropy stable, solver. So with this, I just want to thank you for your attention, and I want to thank the organizer for organizing, this event and inviting me. So in the first picture, this is the most important one, is the one that was taken recently by the I think the International Space Station. You can see Argentina and Buenos Aires, and on the back the moon. It's a true pictures, and on the side it's something, is not a joke. I grew up in Italy with these two fantastic player, especially Claudio Caniggia, who used to play in my team in Bergamo. So this is why I put it for fun here. And with this, Ugo, I'm basically done. I'm ready to take any question if you have.
Thank you very much, Matteo, for the very interesting presentation. Estamos listos para preguntas. Si quieren hacerlo directamente, escribirlo en el chat. Ya existe una. Se los voy a ir haciendo a Mateo. Si hay otra, pueden ir haciendo ahí, o simplemente abriendo sus micrófonos. Mateo, we have one question from Pascual Bruel. He asks, are you doing something specific when dealing with low Mach flow with your compressible solver? You can see the question in the box chat if you want.
I saw it. Thank you, Ugo, and thank you, Pascal. No. So right now, with the results I show you, we are not doing anything specific. We are not encountering any problem, either in terms of, we probably, how to say, we should be careful in the sense that, usually compressible solver, they are not the best, a tool that you can use when you are dealing with low Mach number flow. But because we want to develop a tool that can handle region where the Mach number can be very low and region where the Mach number can be very high, so we want to use a single compressible solver. Despite of that, we have a version in the framework which can handle through, artificial compressibility, incompressible flow. Okay. On that regard, we are working on, how to accelerate the computation of the solution at each time step. But back to your question, for the results I show here for the talk I presented here, we are not doing anything specific for low Mach number flow. And you can see that we were running Taylor Green very, very low. The Formula One car is extremely low, and few other test cases, the Mach number was, basically practically incompressible. I hope I answered to the question.
Yes. Okay. Thank you very much. And so it means that you have no accuracy problem, and you have no spurious mode on order of Mach.
No.
No. So you're
not
over
that we
both
observe,
the hydrodynamic limits and acoustic limit when the Mach number is going to 0, no problem.
Well, we didn't. We went up to 0.05, which is already very low. Okay, we didn't push the limit too much. What I can tell you is that for a plethora of test cases that we run, we didn't observe anything. What I'm also can add is that we have a student who is working on the analysis of the modes at different value of the Mach number and also Peclet number. And because it was also surprising to me that we couldn't see,
yes. And did one or some of these test cases involved acoustic waves as well?
Sorry, can you repeat, please?
Did some of your test cases involve the simultaneous presence of acoustic waves and entropy waves?
Oh yes, in the how to say in the Valeo CD Valeo that you have huge acoustic wave. That test case is mainly we use it because we wanted to provide the acoustic source for then simulating the noise, the aerodynamic noise of it. So that's one of the tests. The other one, sorry.
No, it's quite impressive. Yes.
Okay. So, and then let me think, I'm not sure what, in the Chardin problem, the triangle, where it's supersonic, there you also have, acoustic wave, especially at the beginning, and also entropy waves all together. So I'm not saying that it's perfect, but for those cases where we couldn't see any issue.
Okay, so it's quite, and the type of element you are using, were they simplicial cells or not?
So we only have hexahedral type element, tensor product element. Okay, that's the only element that so far we want to use and deal. And what we do, we can generate mesh with the other type of element, but what we do at the beginning of the simulation, we chop those elements in hexahedral. Okay, so when we generate the mesh, we also need to be careful because we know that we are going to chop it, so they're going to become more finer. So you need to take into account that in the mesh generation basically.
Okay, thank you very much. Very interesting. Thank you.
You're welcome.
Another question. ¿Alguna otra pregunta?
I have a question.
Yes. Sí.
Guillermo. Hi, Mateo. Very nice talk. Thank you so much. This is Rodrigo.
Rodrigo, yeah, I hear you very, very low.
Very low? Oh, no,
is Frank? Frank?
No, this is...
Well, you can go ahead with another question and I will set up my microphone here. Sorry about that.
Okay.
What about now? Can you hear me better?
I can hear you better.
Okay.
At least in Saudi Arabia, we can hear you better.
Okay, that's good. Well, thank you so much, Mateo, for this talk. This is very impressive, all your results. And
thank you.
I just wanted to know, what do you do for when you have an subsonic outlet? What do you do there? Because you're going to have some incoming waves and that can pollute your domain, right?
Yeah. So, I grew up with boundary condition, at least for my postdocs, during my postdoc time. So, right now, what we basically do, we let the Riemann solver to pick up what, we solve a Riemann problem, okay, at the interface with subsonic. So we impose whatever we know from the flow, so basically the full solution, and, we let the Riemann solver to decide what it has to do. Why do we do that? Because we know that things is entropy stable. We can prove that this approach is entropy stable. So it might not be, the best things that you want to do, okay, in terms of maybe, acoustic wave reflection. Nevertheless, again, my answer is the same. For the test cases that we have run so far, we couldn't see any problem by imposing the boundary condition in this way, okay? So we don't have strong wave reflection, even though we run problem for generating the source of acoustic noise like the CD Valeo. We got, the noise the broadband spectrum of the noise, matching, very well compared to the experimental data. We do something very specific for wall boundary condition, because that was really one of the weakest link in the chain of entropy stability. So you need to carefully handle wall boundary condition. But for subsonic, we just dealing with the Riemann problem.
Right, thank you.
Welcome.
Yeah.
Santiago said,
yeah, that's
how is your
question
performance in
chat.
terms of computing time against second order code in the last slide? You mean this one with Caniggia? No, I'm joking. Sorry. Wait. The last slide. You're talking about this, Santiago, right?
Yes.
So how is your performance in terms of computing times again? Okay, so I can tell you that it's a famous code that we were comparing with, that it's used also in a startup company, and the number that they are getting for a CFN number of 1.2, I think it's about something like, we have 22,528. In their case, it was 29,923, something like that. So we are basically, it's the same number that we are getting. Did I answer to your question, Santiago? Yes. Okay. Good.
Yes.
Thank you.
Okay. Is no other question. We thank you.
One.
Oh,
I have one.
Go ahead. Go ahead.
Sorry. I want to know, in the case of the F1 wing, that is very complex and it's very, very hard to mesh, how do you chop the mesh with the hexahedral?
Okay, so for that mesh, I don't have the mesh here, I think. What we end up having is to generate the mesh. So what Formula One McLaren, I'm talking about McLaren, they use what we call CAN software, commercial software like ANSYS, Star CCM, and so on and so forth. But they also used in the past the Nectar++. So the Nectar has this, neck mesh generator that can, read the CAD geometry and generate high order, hexahedral element. So what we end up doing there, tetrahedral element, sorry, that then you can, merge to generate hexahedral element. So that's what we end up using with McLaren for these things, and then we chop them in hexahedral. For the imperial front wing, which is an easy variation, a simpler variation of that wing, we simply use pointwise 18.2, of course, a legal version, and that's what we did. But again, it's not an easy task. If you let the solver run, wild to generate the mesh, you're going to get, tests, prim everywhere. So you need somehow to control it. So that is a drawback. I know, but it's, right now it is beyond our, list of goals or target.
Okay. Thank you. Thank you very much. Nice work.
Thank you very much.
Okay. If there are no more questions, we thank.
I have one more. If there
okay.
No one showing up for questions, so I have just one more. It's again Rodrigo Mateo here.
Okay. Yeah, I can hear you.
Okay, so what did you do? I mean, when you mark those terms in red for geometrical conservation law, is something that you have to add to
you mean this
to the formulation, or yeah, it's something that you add to comply with the
no. So no, okay, so this, it's something that you do pen and paper. Here I'm at the continuous level, and analytically those terms, if you try to compute them with pen and paper, even symbolically, they goes to zero. So okay, so at the discrete level, where is it? Here at the discrete level, okay, if you take the equation in the split form and you discretize it, what you end up having, you have, you have this term. But if you have this term, you cannot preserve the free stream preservation. So you want to construct your You have your operator D here, which is given by the SBP operator. So what you need to compute or to construct, that's the minimization problem I was talking about. This quantity in such a way, the sum of the derivative of those terms, times the unit vector 1, they give you 0. Those are the
that's right.
discrete counterpart of the geometric conservation law constraint. So you basically you want to construct your algorithm to have that properties. Otherwise, if you take a box, you inject uniform flow, there is no body inside. You're expected to preserve uniform flow, right? You will start to see that in the long run, you will generate something which is no longer uniform flow. So if you monitor the residual is not machine precision, but start to grow. It's like you have, those are adding, they act like source term. It's like a tiny, small source term.
All right. Well, thank you. Yeah.
Welcome.
All right, Guillermo.
Hugo, question or we're done?
¿Alguna otra pregunta?
And so sorry, and this the question of Rodrigo in regardless with regard with this question, this effect is due to the incompressibility. Is the lack of incompressibility, or what is the reason?
You mean this term?
Yes.
No, what do you mean? I mean, so let's go back that maybe here it can easily, those are called geometric conservation law term.
Yeah.
Simply because it's geometry. It has nothing to do with so maybe I should have, can you see my mouse?
Yeah.
What is actually 0, I should have been more careful, is not AMU. You can pull out AMU outside of the summation. What is 0 is the sum of partial with respect to xi of the sum of j d xi dm. Those are the sum of those terms are 0, and they are purely geometric.
Okay, I see. Okay, thank you.
Welcome.
Okay. I'm not seeing any more questions in chat. So, Mateo, we thank you once again for your.
Thank you very much, Mateo. Thank you very much.
Thank you very much to all of you. I will stay online. Have a good continuation of the Congress. It was really my pleasure.
Please do.
Well, I have a lot of questions for Mateo, but
maybe
we're gonna leave that for another meeting. I mean,
who's this? I don't. What's your name? So I will come and look for you.
Rodrigo Paz.
Rodrigo. Okay.
Okay. Well,
okay.
Bye, guys. It was a nice talk.
Bye, Rodrigo.
Good to see you.
Thank you very much. Bye, Hugo. Thanks a lot.
Bye, Mateo. Continuamos el Congreso a partir de las 2 de la tarde con las sesiones. Y tenemos una keynote en la sesión de mecánica de fluidos a cargo de Laura Morales. Y por la tarde tenemos una plenaria por parte del profesor Auruch. Entonces,